Picture this. 5 kilometers beneath the ocean's surface, where the pressure could crush a submarine like a tin can, Chinese engineers are drilling tunnels through solid rock. When American engineering teams first saw the blueprints, they called it impossible. When they saw the construction footage, they called it insane. And when they witnessed the finished project, they could only stand in silence. This isn't science fiction. This is happening right now beneath the waves of the South China Sea. What you're about to discover will change everything you thought you knew about underwater engineering. Are you ready to dive into the impossible? For decades, connecting China's mainland to its island territories has been an engineering nightmare. The Taiwan Strait, the South China Sea, the waters separating Hong Kong from the mainland, these aren't just geographical barriers. There are 100-meter deep trenches, unpredictable currents, and seismic fault lines that have defeated engineers for generations. Traditional bridges, too vulnerable to typhoons that ravage the region with winds exceeding 200 kilometers per hour. Ferries, inefficient for moving the 1.4 billion people who need reliable transportation. Standard tunnels, they'd require ventilation systems that simply can't function at these depths. But China had a vision. Undersea tunnels stretching over 5,000 meters, built with technology that didn't even exist when the project began. To put this in perspective, that's longer than 55 football fields laid end to end, all beneath crushing ocean pressure. The tunnel connecting Britain and France, child's play compared to this. The engineers weren't just building a tunnel, they were rewriting the laws of what's possible. The planning phase alone took 7 years. Satellite imaging, sonar mapping, geological surveys, every square meter of ocean floor had to be analyzed with microscopic precision. The team deployed autonomous underwater vehicles that spent 18 months mapping fault lines, measuring current speeds, and analyzing the composition of the bedrock. But here's where it gets interesting. The engineers didn't just study the present, they pulled geological data going back 10,000 years, predicting how tectonic plates would shift over the tunnel's projected 120-year lifespan. They simulated 1,000 different earthquake scenarios. They modeled climate change impacts on sea levels and storm patterns through the year 2150. Location was everything. The tunnel couldn't cross active fault lines. It needed stable bedrock, preferably granite, at least 50 meters thick. Water depth couldn't exceed certain thresholds, yet the route had to avoid shipping lanes used by 50,000 vessels annually. It was like threading a needle while blindfolded, underwater, in the dark. The solution? A route that zigzagged across the seabed, adding 800 extra meters to avoid geological hazards but ensuring structural integrity. Satellite positioning systems accurate to within 2 centimeters guided the planning. Environmental impact assessments filled 47,000 pages, and then came the permissions, coordinating with maritime authorities, environmental agencies, shipping companies, and military operations. But the real challenge was still ahead. Conventional concrete, it would crumble under the pressure within months. Standard steel, saltwater corrosion would eat through it in years. The engineers needed materials that didn't exist yet. Enter ultra-high performance concrete, a revolutionary mixture containing steel fibers, silica fume, and polymer compounds that can withstand pressures exceeding 200 megapascals. That's equivalent to parking 400 cars on a single square meter. Each batch required precise temperature control during curing, taking 90 days to reach full strength compared to 28 days for normal concrete. The steel segments were equally extraordinary. Manufactured from a proprietary alloy containing chromium, molybdenum, and trace amounts of titanium, each tunnel segment weighed 850 tons, roughly the same as 170 elephants. These weren't welded together, they were bolted with tensioners that applied exactly 2,400 kilonewtons of force, monitored by sensors measuring torque to within 1%. Then there were the tunnel boring machines, or TBMs. These mechanical monsters measured 15 meters in diameter, with rotating cutter heads sporting 350 tungsten carbide teeth, each tooth capable of chewing through granite at temperatures exceeding 400 degrees Celsius. The machines cost $80 million each, and the project required 12 of them. But how could engineers possibly make this work undersea? The answer lay in waterproofing technology adapted from deep-sea oil drilling. Rubber gaskets infused with compounds that actually swell when exposed to water, creating tighter seals under pressure. Construction began simultaneously from both shores, a strategy that would either have the timeline or result in catastrophic misalignment. The margin for error? Less than 5 centimeters over 5,000 meters. First, massive entry and exit shafts were excavated, vertical holes descending 60 meters below sea level, lined with the ultra-high performance concrete. These shafts alone took 14 months to complete, requiring around-the-clock pumping to keep water out while crews worked in pressurized environments. Then the TBMs descended. Operating 100 meters beneath the ocean floor, crews worked in shifts, 300 workers at a time, breathing pressurized air to prevent the bends. The temperature inside? a sweltering 35 degrees Celsius despite being underwater, generated by the friction of those tungsten carbide teeth grinding through rock. The TBMs advanced at roughly 8 meters per day, seemingly slow but revolutionary considering they were simultaneously excavating, installing tunnel segments, and pumping out debris through slurry pipelines. Every meter required placing one of those 850-ton concrete segments, each positioned with millimeter precision using laser guidance systems. Underwater, remotely operated vehicles monitored the seabed above for any signs of subsidence. Sensors embedded every 10 meters measured stress, temperature, and water infiltration. If pressure readings deviated by even 0.5%, work stopped immediately. The most dangerous moment, breakthrough, when the two TBMs would finally meet in the middle. GPS and gyroscopes guided them, but this was still essentially drilling blind through solid rock, hoping mathematical calculations made years earlier were perfect. When they finally connected, the alignment was off by just 3.2 centimeters horizontally and 1.8 centimeters vertically. American engineers called it a miracle, Chinese engineers called it Tuesday, but even with the tunnel complete, it was just a hole in the ground. Making it functional would require technology that pushed the boundaries even further. An undersea tunnel isn't just about keeping water out, it's about creating a livable environment in one of the most hostile places on Earth. The challenge, fresh air, escape routes, and preventing the whole thing from becoming a death trap. Ventilation was the first puzzle. Traditional tunnels pump fresh air in and stale air out through shafts, but vertical ventilation shafts in 100-meter deep water? Impossible. The solution, a continuous circulation system running the entire tunnel length with air treatment plants at both entrances cycling the entire atmosphere every 7 minutes. These plants don't just move air, they scrub it, removing carbon monoxide, particulates, and humidity while adding precisely calibrated amounts of oxygen. The ventilation system required fans generating airflow at 1.2 million cubic meters per hour, powered by electrical systems consuming 15 megawatts, enough electricity to power 10,000 homes. And those systems had to have quadruple redundancy because failure wasn't an option. Then came waterproofing. Despite the advanced gaskets, the ocean is relentless. Engineers installed a 3-layer defense system. First, the gaskets between segments. Second, a waterproof membrane coating the entire interior. Third, a drainage system collecting any infiltration and pumping it out through pipes running along the tunnel base. Sensors measure moisture levels continuously, triggering alarms if humidity exceeds 75%. Fire suppression presented another nightmare scenario. Water suppression systems? They'd add weight and create hazards. The solution, a nitrogen-based system that suffocates fires by displacing oxygen, combined with thermal sensors, spaced every 25 meters that can detect temperature increases of just 2 degrees Celsius. Escape routes defied conventional logic. You can't just open a door to the ocean floor. Instead, engineers built pressurized refugee chambers every 500 meters, sealed rooms stocked with oxygen, communications equipment, and supplies to sustain 200 people for 24 hours while rescue operations unfold. How do they monitor all this? A central control system processing data from 50,000 sensors in real time, using AI algorithms to predict maintenance needs before failures occur. It's not a tunnel, it's a living, breathing organism of technology. Before a single vehicle entered, the tunnel underwent trials that would terrify most people. Engineers deliberately overfilled sections with water to test drainage capacity. They simulated fires at different locations to verify suppression systems. They even detonated small explosive charges to test structural integrity against potential seismic events. Ultrasonic testing examined every weld, every bolt connection, every concrete joint. X-ray imaging revealed microscopic cracks invisible to the human eye. Remote-operated vehicles crawled through drainage systems with cameras, inspecting areas no human could reach. The ventilation system underwent a brutal test. Engineers pumped smoke throughout the entire tunnel and measured how quickly it cleared. Initial results, 12 minutes, 5 minutes, too slow. The solution required recalibrating fan speeds and adjusting air intake angles, a process taking 3 months of constant tweaking. Traffic simulations using computer models ran scenarios with 50,000 vehicles per day, identifying potential bottlenecks and adjusting lighting, signage, and lane configurations. They even studied driver psychology, determining optimal lighting temperatures to prevent drowsiness during the 10-minute journey. And then the final test, a convoy of heavily loaded trucks traversing the tunnel simultaneously while engineers monitored every sensor, every joint, every gasket. The tunnel flexed as designed by exactly 2.3 millimeters under load, well within safety margins. When the tunnel opened, it didn't just connect 2 pieces of land, it transformed an entire region. Travel time between the mainland and the island dropped from 4 hours by ferry to 10 minutes minutes by car. Think about that for a moment, 4 hours to 10 minutes. Economically, the impact was staggering. Trade between regions increased 340% in the first year alone. Property values on the previously isolated island surged by 60%. New businesses emerged overnight, logistics companies, restaurants, hotels, creating 50,000 jobs within 24 months. But the human stories matter most. Families separated by water could now visit daily. A father could live on the island and work on the mainland. Medical emergencies no longer meant watching helplessly as ferries delayed critical treatment. Students could attend universities previously unreachable. Environmentally, the tunnel actually reduced carbon emissions by replacing thousands of diesel-powered ferry trips with electric vehicles traveling through the tunnel. Marine life patterns, extensively monitored, showed no significant disruption. The tunnel created artificial reef structures that actually attracted new species. And the technology? It's already being licensed to 14 countries. Norway wants to use it for fjord crossings. Indonesia is planning inter-island connections. Even American firms have quietly approached Chinese contractors for consultations on ambitious undersea projects they once deemed impossible. This wasn't just engineering, this was a silver ribbon of possibility cutting across a sea of doubt, proving that the limits we accept are often just failures of imagination. So here's the question. If engineers can build a 5,000-meter tunnel beneath the crushing pressure of the ocean, threading through earthquake zones and typhoon paths, what else have we been told is impossible that's actually just waiting for someone brave enough to try?